You have probably seen matrices before, maybe just as grids of numbers in a math book. Something you multiply with or plug into a formula called a determinant. Boring, right? But linear algebra, the math behind vectors, scalars, and matrices, is way more than just number crunching. What if I told you those matrices are actually transforming space like they are just bending the whole vector space? Let's start simple with a 2D vector. This arrow goes 3 units in the x direction and 2 units in the y. Vectors like this can represent movement, direction, even forces in physics, written just by a simple column or a vertical matrix. Now add a third number to it, and we are in the 3D space. This vector moves through space. Vectors aren't just numbers. They are how we describe motion, structure, and position in the world around us. So, what happens when we multiply a vector by a number? We stretch it or shrink it or flip its direction. That's called scalar multiplication. It changes the size but not the direction of a vector. But what if we want to rotate it or flip the whole space? Now here's the fun part. A matrix doesn't just transform one vector. It transforms all of a space. It moves the grid itself. Starting from the basis vectors of I and j, the axis tilt, and every single vector follows the new rules. That's a linear transformation. That's what matrices do. And some special ones like orthogonal matrices rotate or reflect without stretching or distorting. Kind of like turning a shape without changing its size. Now watch what happens when we apply a 3-dimensional transform. The red, green, and blue basis vectors, the ones that define the x, y, and z axis after the matrix, they point somewhere new and that becomes our new space. Everything else moves in sync. So, what does the determinant tell us? It tells us how much the area or volume scales under transformation. A determinant of 0, that means space collapses, the whole thing gets flattened. And in 3D, the determinant tells us how a cube becomes a stretched box, a parallelepiped. If it flips orientation, the determinant turns negative. If it stretches, it grows. If it collapses, it's gone. So, no, matrices aren't just arrays of numbers, and the determinant isn't just a formula. They are telling you how space behaves, how it stretches, collapses, or flips. This is linear algebra, and this is just an introduction to it. That was a lot of arrows, grids, and transformation. But what uses all of this in real life? Well, it turns out linear algebra is exactly what powers the language models we use every day. In models like ChatGPT or Google Gemini, each word is represented as a vector, not in 2 or 3 dimensions, but in hundreds. These are called word embeddings. Words that are similar in meaning, like walk and run, end up with vectors that are close together, and the relationships between words can be understood as vector operations. For example, take the vector for king. Subtract man and add woman. The result points to the vector for queen. That's not just language. That's geometry of meaning. And it's all thanks to high-dimensional vector spaces, matrix multiplication, and linear transformations. So yeah, what looks like math homework is actually behind how large language models understand you. Linear algebra isn't just useful, it's everywhere and you are just getting started.